Hey kids, welcome back. We'll continue our lesson on our unit on electro electric charge, or more specifically electrostatics. This is gonna be a longer lesson, so we can split it up in two parts. There's a lot of information, but it's not super important information, so you can keep working on any labs and projects I might have assigned last week. So let's start with this problem. Good job. It's choice three, because choice 3 is the only one that's divisible by the elementary charge 1.6 times 10 to the negative 19 coulombs is the charge on a proton, and it's also the opposite of the charge of an electron. And electrons are what we mostly care about in this lesson and unit in general. Okay, what's going on today? Check this out. Ta-da! Static electricity. Okay. Um, I didn't really talk about it yesterday, but the first way objects can get charged is by what you just saw, rubbing them together. If you rub two objects, you will see sometimes one become positive and the other becomes negative. You will always see both together. You will not have both become positive or both become negative or one become negative, one stay neutral. And you have to have two objects. Why is that? What makes sense? Why is that? Obviously, for this charge by rubbing, also known as triboelectricity, um, electrons transfer from one to the other. In the example we just did, electrons went from my hair to the balloon. And the reason why is because I looked up in the table. I looked it up in the triboelectric series. Some materials, when you rub them, tend to gain a positive charge by losing electrons, and some tend to gain a negative charge by gaining electrons. Rubber balloon tends to gain electrons, hair tends to lose electrons, so the rubber balloon became negative, and due to reasons, it stuck to the wall. So this is the triboelectric series. Obviously, not something to memorize, but it does explain why sometimes things will get charged by rubbing. Like if you ever put on a sweater and then touch a doorknob and get shocked, that's why. Okay, you might notice there's no metals. If you want like a rule, it's not like a strong rule, but you could say that natural materials tend to lose electrons, and the more like synthetic materials tend to gain electrons. But that's not like really a strict rule. You don't have to. You don't really need a rule. You can look it up if you ever need it. But you might notice there's no metals. I don't see copper. I don't see iron. I don't see steel. Any idea why there's no metals on the triboelectric series? Some longer, more in-depth triboelectric series might have metals, but they're usually in the center. And also, what do you learn about metals in chemistry? They're conductors. Yeah, good job, Bunny. They are conductors. So even if you did rub two metals or something else in a metal, and the metal got charged, the electrons would be free. They would just flow away from the metal. And we'll talk more about that later. So you don't really see metals get charged by rubbing. The first method of charging is rubbing, and that's usually for insulators, not conductors like metal. I should probably write it down, but I'm kind of lazy. You should know for chemistry. Insulators don't conduct charge. Conductors do. Metals are conductors, they do, because they have free electrons. Water is actually not a conductor, it's an insulator. But most water has salts or other dissolved substances inside it, and in that case, those can flow, and that will make it a conductor. But for physics, we'll stick with solids. Metals are the only conductors. Everything besides metal is an insulator, pretty much. So the first method of charging is rubbing. That's how lightning storms form. The clouds rub on the air and they build up charge. Okay, now let's do a thought experiment. Close your eyes. Imagine it's 2 years ago. There's no COVID. Mr. Lamb is not balding. There's no pandemic. Imagine where you have a brand new subway system where each car has 4 seats. Okay. This is a great analogy. Don't worry. It's coming. It's gonna be good. Imagine you stay after school for a long day of studying in physics club, and you're so enthralled by physics you miss the bus, and you gotta take the subway home. So first you walk to Mashalou to get pizza, and then you get on the subway, and Mashalou's like the second last stop. So when you get on, there's almost no one there. You get in, you have a seat right there. And then the train goes. That's what trains sound like. Goes next station, and then there's one more person, and you're right here in one seat. There's 3 other seats open in your train, and there's 4 seats, a whole train empty right next to you. But the person comes and they stand right next to you, right in front of your seat. They're standing. How would that make you feel? Obviously, this is pretty sus. Luckily, there's no pandemic in this scenario, but people on trains like to spread out because people on trains usually they kind of smell bad. They want to smell. They usually smell bad. So this would never happen. One person will get on the train. Let's just stick with one train so far, one car so far. The next person will come in and they'll sit as far away as possible. Then someone else will come in and they'll sit as far away as possible. And the next person will come in and they'll sit as far away as alone from everyone else as possible until all the seats are filled. And then after that, obviously, you've been on the train. People will still come in even though the seats are filled. So they'll stand, but they'll still stand as spread out as possible because they smell bad. No other reason. But that's just a rule of life. Okay. So in this analogy, the seats are protons and the people are electrons. Why? Because protons can't move and electrons can. If you remember chemistry, the protons were the nucleus. They're attached to neutrons. They're bonded together. They'll never move. But for metals, conductors, electrons are free to move. They can move. And they all spread out. Why do electrons spread out? I said people spread out because they smell bad. Why do electrons in a conductor spread out? Yes, Bunny? Why do electrons spread out? Because they all repel, because they're all negative. Yeah, great job. They're all negative. Negatives repel negatives. Electrons will spread out, just like people on a train. Okay, so back to my amazing analogy. Let's say I have a super crowded train car. There's 4 seats, and again, there's 8 people. 4 people sitting, 4 people standing. It's a pretty packed train. What if I magically connect a new train car with only 4 people inside? So this car has 4 seats, 8 passengers. This car has 4 seats, 4 passengers. And obviously, you never want to cross through the train tracks, through the train cars while it's moving. But if it stops at a station and all the doors open and these people have time to spread out, what are they going to do? They'll spread out. 2 people from the crowded train car will go to the not so crowded train car. Even though this train car on the right is full, 4 people, 4 seats, this train car is like over full. It's super crowded. So these people are like, oh, it's so crowded in this train car. There's 4 more people than there are seats. I go to the other train car. Even though there's no free seats, there's still more space. If I go over here, there'll only be 2 more people than seats. So it'll still be less crowded than the train car I'm in, and then they will move. So yeah, they'll spread out. All right. If seats are protons and people are electrons, what are the charges of the train cars before they connect and after they connect in terms of E? That was probably a very weird statement. So let me break it down. Before, this train car had 8 passengers, 4 seats. That's 8 electrons, 4 protons. So the charge would be -4 times E. Technically, it's -6.4 times 10 to the -19th coulombs. But I'll leave in terms of E. E stands for elementary charge. Okay, and then this car had 4 electrons. Okay, I'll use E for elementary charge, E minus for electrons. Problem solved, lesson saved, good job. And 4 protons, Q equals 0. After 2 people move train cars, they both have 6 and 4. So, if you have a lot of negative charge, it'll spread out. Yeah, it went from -4 and 0 to -2, -2. The charge spread out. Since electrons all repel each other, negative charge will spread out, but only between conductors when electrons are allowed to flow. Electrons will spread out to distribute charge evenly. But protons can't move. So what if if a negative object touches a neutral object, the charge will spread out. Protons can't move. So tell me what you think. If a positive object touches a neutral object, will the charge spread out? What will happen if the first car was positive instead of negative? What if it had more seats than people instead of people than seats? Tell me what you think would happen in that case. Let me draw it out to make it a little clearer. This train car is still full. There's 4 people, 4 seats. Before, this car was overcrowded, so it's negative. Now it's undercrowded. There's only 2 people in 4 seats. So before, this has 2 electrons, 4 seats. The charge is plus 2. This has 4 and 4. The charge is 0. Okay, so here's the question. Last time, negative charge spread from the left car to the right car, or left object to the right object. This time, will positive charge flow from the left object to the right object? What do you think, Bunny? No, Mr. Lamb, because you said protons can't flow. Well, you're wrong. This car is positive. This car is neutral. When they touch, when they're connected, or when the train goes to the station and stops, positive charge can't flow from left to right because the positive charge is the seats, the protons. They can't move. We established that. But don't look at the left car, look at the right car. The right car will say, it's crowded in here and less crowded over there. If I just walk on over, I'll be in a less crowded car, and that's what will happen. One person will go from the more negative object to the more positive, because electrons want to spread out. Hello, test, hopefully it works. Okay. Even though there's enough seats here for everyone, there's still more space. So one person will still flow on over. So, positive charge can't move. That is true. But if you touch a positive object to a neutral object, just like touching a negative object to a neutral object, charge will flow to balance out equally. It's not positive charge flowing left to right. It's actually negative charge flowing the other way. But no matter what, if 2 conductors touch, the charge will evenly distribute between them. This is known as conduction. Charge will always flow to even out, assuming they're both the same size, assuming they're both 2 identical train cars. That's how the charge went from unbalanced to balanced, because electrons spread out evenly. Okay, there's a lot of questions, but that's fine. We can do it. Hopefully my headset will last. Okay. Let's say we have another crowded train car. Let's say it's very crowded. Oh, there's so many people in this train car. It's so smelly. It's full of stinky people. And let's say, there's a new train car that's brought in, but it's humongous. It's not a train car, it's a cruise ship. It's so, oh my god, it's the biggest cruise ship ever seen. It has 1,000 seats, and each of those 1,000 seats has one person. Okay, so what's this saying? This is saying, what if a charged object is touched to a very, very large neutral object? Remember, the dots are electrons, and electrons want to spread as much as possible. So if I touch a very crowded train car to a very large neutral cruise ship, and the electrons want to spread out, what will they do? How many electrons will leave this crowded train car and go into this cruise ship? Tell me right now. Okay. The answer might be confusing. It's kind of hard because can't really get any feedback. But a lot of people will go from this crowded train car into the big giant cruise ship. Even though the cruise ship is full, there's still more space than there is here. And if the cruise ship is big enough, there'll be only 4 people left in the 4 seats. Assuming the cruise ship is humongous, I just didn't draw the rest of it. People will spread as much as possible. If the cruise ship had an even number of people and seats, and it was much, much bigger than the train car, they'll evenly spread out until it's basically 1-to-1 throughout. It won't actually be 1-to-1 because there will still be more people than seats because there were more people than seats originally. But if that slight imbalance is spread out over a large, large area, it's effectively nothing. I know this is really confusing. I know you're going to go to breakers and say, hey, did you watch the video? Yeah, except it made no sense. Yeah, I know. Oh man, what do we do? Okay, but please. This is what happens when a negative object or a charged object touches the wall or the ground or your finger or anything. You might know like, oh, if I rub my feet on the rug, I can like shock my sister with my finger. But you can't do it again. And you can't like rub your feet. If I like decide I'm gonna just like become like a new Spider-Man villain, and I'm just gonna be like, I'll just rub my feet for 5 minutes when I come home every day until I become like a supercharged super villain, and I can electrocute people with my finger. That's not gonna work. That's not gonna work out. You can't just build up charge forever. If you're charged, you touch the wall, and the wall touches pipes, and pipes touch the ground, and ground touches the whole earth. Remember, charge wants to spread out. So if you try to charge yourself up to super evil shocker levels, as soon as you touch anything neutral, charge will leave your body and will spread out to the object. You can rub your feet on the rug for like hours and hours and hours, but then if you go open the door to your apartments, the charge will leave your body and go in the door, and then leave the door, go to the wall, then leave the wall and go into the ground, and the ground is the whole Earth. It's so much bigger than you. Because it's so big and so spread out, you'll effectively have zero charge left over in your body. No matter how much charge you had left in the beginning, when you touch something that touches something that touches something that touches the Earth, you're basically neutral. The word is you're grounded. This is why most things in life are not charged that much. They have to get charged and not touch anything. If I comb my hair really hard, I have to like put my comb in like a vacuum chamber and not touch it. Because if I put it down on my sink, the charge will go into my sink. If I put it in my other hand, it'll go into my other hand. If I put it in my medicine cabinet, it'll go into the medicine cabinet. No matter where I put my comb, the electrons wanna spread out. And they're gonna spread out, and when they spread out to something really big, the charge in the comb will be effectively zero. That's called grounding. I'm gonna keep going. Feel free to take a break, or feel free to already have taken a break a while ago. Okay. If you want to tell if something's charged, you can use an electroscope. Pretty straightforward. Electroscope, it measures charge. There's two kinds, the leaf type and needle type. Here's the needle type. Needle type is basically a curved piece of metal and a needle. So if you want to tell something's charged, you can take that object. I don't know what this is supposed to be. It looks like a pen with like a pencil head going the wrong way. Never mind. This object with the weird handle is negative. If you touch the negative object to the top of the electroscope, it will conduct, charge will flow. So this object's negative, it'll make the top negative, that'll make the curved piece negative, that'll make the needle negative. What's important is the bottom right here. If the curved piece is negative and the needle is negative, the needle will repel the curved piece and the needle will move farther away. The needle will turn more. So a needle type electroscope, it turns when it's charged. This is true for negative, but if you think about it, it's also true for positive. If this object in the top right were positive, it would pull electrons away, and that would make both the curved metal and the needle both positive, and positive repels, just like negative and negative. So it'll still rotate. So it'll rotate if you touch it with something positive or negative. That's true for the leaf type too, but we'll see that in a little bit. So let me draw it out here. I have a large negative object. Here's an electroscope. If it's not rotating, it's neutral. If I touch the big negative rod to the electroscope, that'll make this negative, and the needle negative too by conduction. But if the needle's negative and the curved part's negative too, it'll rotate to repel. And that's how the electroscope will measure a charge. If this rod were positive, the same thing would happen, except instead of electrons going this way, they'll go this way. But the needle will still rotate, and it'll still look the same. So we covered charge by conduction and charge by rubbing. There's one third thing, and it's very, very unintuitive the first time you hear it, but it shows up on the reagents all the time, so let's do it. We did charge by rubbing, charge by conduction, now charge by induction. And because it's definitely working, let's go back to the train analogy. Let's say we have two train cars, they're both neutral, they're both even, they both have 4 seats, 4 people. But right behind this train, up pulls a gigantic garbage train. Those are stink lines because the garbage train smells bad. It's full of garbage. For some reason, these trains are drawn from a top view. This is a side view, but that's okay. A big stinky train car pulls up right next to the trains. Not touching. If it was touching, that would be conduction. But they're not touching. So these people all spread out because they smell bad. But if there's a gigantic smelly garbage train right behind them, what might they do? Yeah, sure, people smell bad, but compared to a giant garbage truck, it's not that bad. All the people, they want to get as far away from the bad smell as possible. They'll all crowd in to the far side, away from the garbage. Now, what will happen if I take away the garbage truck and then I take away the connection? If I take away the garbage truck, then the people will spread back out. And then if I take away the connection, it'll be neutral. Same as before. No change. Nothing got charged. New question. What if I bring in the garbage truck, the people go to the far side, and I reverse the order? What if I remove the connection and then the garbage truck? So I leave the garbage truck, I remove this, and then I remove the garbage truck, not the other way around. I remove the connection, and now I remove the garbage truck. So now these people, they're crowded. They want to spread out, but they can't because it's not connected. There's no more conductor. Now these people are stuck in the stinky car because they went into the stinky car to escape the stinky truck or train or whatever I said. But they can't go back. So this is charged now by induction, not conduction. It's called induction because the big stinky train full of garbage never touched this car. But still, it moved the charges around. A really weird analogy. Let me try to do it in terms of real physics. Here I have two pieces of metal. They're both neutral. So there's pluses and minuses. Plus, minus, plus, minus, plus, minus, plus, minus, plus, minus. And I bring something super large and super negative very close. All the pluses can't move, but all the minuses can. These minuses, they are repelled by these minuses, but not as much as they're repelled by this gigantic negative blob. So, all the minuses will go to the far side, or not all of them, but a lot of them. Then, the important thing is you remove the connection before you remove the negatives. So first, disconnect these. Then, remove this. Now this right rod is negative. It has way too many electrons. They want to spread out. They want to spread back to the left rod, but they can't because it's not attached. The right rod was charged by induction. And so was the left rod too. The right rod became negative and the left rod became positive. But the charge wasn't conducted from the third object. It was inducted from the third object. Pretty long lesson. Do I have anything else to say? I'm sorry. don't hate me too much, please. Or don't hate me anymore. I mean, just a normal amount, it's fine. Yeah, that's just about it. So here's a picture to show you one last time. They switched the sign on me, but it's fine. If I bring a large positive object near a leaf type electroscope, this positive pink rod attracts all the electrons. So the bottom is the leaves, that's what they're called. It's just like a little piece of foil or something. It pulls all the electrons because electrons are negative. They want to get close to the positive. So the electrons leave the leaves, go to the top. That leaves the leaves positive, and they will spread out. So the two electroscopes, there's needle and leaf. The leaves will repel when it's charged. The needle will rotate when it's charged, but they can be charged by induction or conduction. And I'm happy to go over it again in class if you're confused. But it's actually not on the AP, and and it is on the Regents, but it's kind of annoying and not really helpful for anything else. So just a few practice problems. You can work on the other stuff too. I'll see you guys in class.